Hey friends, today we're going to go over section 1.7, which is representing absolute value as a distance. And our goal today is to solve absolute value inequalities, and we are going to talk about some equations too. But we're going to stop doing that crappy algebra stuff where we just do all this random like, oh, I'm going to write two equations and set one equal to 7 and set its opposite equal to 7. That's great and all, and I'm glad you all can do that. But today to me is way more important. And just as a preface, in my opinion, this is single-handedly one of the most important lessons if you ever plan on taking calculus. I know that's a long way away, but representing an absolute value as a distance becomes the foundational understanding of what we call a limit in calculus class. So really the reason of doing this is to support further work as well as our current content. There's a bunch of words there on the notes you're welcome to read. I think my words are better than that, so I'm going to speak them. On a number line, distance is always measured by subtraction. So for instance, if I draw a quick number line, here's 0, 1, 2, 3, and 4. There is absolutely no argument that the distance between 1 and 4 is 3 units, right? So 4 minus 1 is equal to 3. But it shouldn't matter the order in which we subtract. The distance between two numbers should always be the same. And we know that distance can never be negative. What we start to interpret distance as on the number line, or I should say the sign on the number line, is what direction we're traveling. But to account for that, we just use absolute value to measure distance. So our foundational understanding today is this. The absolute value of x minus a number is equal to d is always represented by a sentence. And even more so, you can see that sentence there. The distance between this thing and this thing is exactly d units. So let's look at where this stuff comes from. The distance between that phrase literally translates to the absolute value sign and the minus. If there's no minus there, you are not measuring distance. X, we can clearly see, is right there. And A, we can also clearly see is right there. So just in general then, we can say whenever we see these symbols, the absolute value separated by a minus sign, there's going to be something here, and there's going to be something here. And we translate that into the distance in between those two things. So our goal for today is to solve these absolute value equations and inequalities without ever writing an equation that we would think of before. So first of all here, our goal is to rewrite the problem as a sentence. So here, I'm not going to use that. I'm going to use the sentence that I prefer. We're going to graph the solutions and then write our solutions using set notation. So here, first of all, we should notice instantly out of the gates, it's not using subtraction. So I'm going to rewrite that using subtraction, x minus a negative 3. That's equal to 7. So let's trace back our formula. We see the absolute value signs and the minus, which give us the distance in between. That first thing that's listed is x. That second thing that's listed is negative 3. And then it tells me what this distance is equal to. It tells me the distance is exactly equal to 7, right? Because this phrase here is a measurement of distance. So all I have to do on the number line, 1, 2, 3, there's negative 3. Actually, I'm going to rewrite. I'm just going to put negative 3 in the middle. What I want to know is what number, x, I don't know what that is yet, but whatever x is and negative 3 are 7 apart. Well, if I know where negative 3 is, why don't I just travel 7 away from that? If I travel 7 to the right, that brings me to the number 4. If I travel 7 to the left, that brings me to the number negative 10. So I instantly know then that the solutions here, what numbers are 7 away from negative 3, that's negative 10 and 4. And in our set notation, I'm okay with us just putting it like that. Let's move to another one. I'm going to add one here. Let's look at the absolute value of x minus 3 is equal to 9. Okay, well, it's written as a minus sign. So if I think about this little sentence, the first thing before the minus sign was an x. So the distance between x and this number 3 is exactly equal to 9 units. Well, I don't know where x is, so I can't place that on the number line, but let's place 3 on the number line. Because if I know where one of the numbers is, the other ones are 9 away. So if I go 9 this way, that brings me to 12. If I go 9 this way, that brings me to negative 6. So the solutions to this equation are negative 6 and 12. Now, as we move forward, we have an inequality now, and that's really our goal for today. Section 1.6 was just algebraically finding these things out, and I would encourage you to take a moment to solve that algebraically like you normally would by writing two equations. And I hope you see that this is a lot easier, in my opinion. Let's move on to this one. So again, we see the absolute value symbols, and they're separated by a minus sign. So that translates to the distance in between. So what are the two things? And if you don't have colors, right, you could probably just use some boxes. That's one of them. This is the other one. So the distance between x and 5 is not exactly equal to 9, is less than 9. Okay, well, if I have two numbers, x and 5, I don't know where x is. So all I can do on my number line is place 5. Now, the solutions to this inequality are not exactly 9 away, but that'd be a great starting point, right? If I knew the numbers that were exactly 9 away, so like 14, if I go 9 to the right, if I go 9 to the left, that would be, -4. So those numbers I'm going to put an open circle on because they're exactly 9 away. I don't want exactly 9 away. I want less than 9 away. So if I have less distance, I should get closer to something. So if I'm measuring the distance between 5 and this endpoint, and I want it to be less than 9, I should get closer to 9. So any of these numbers, 14 doesn't work, but every number before 14 is less than 9 away. Same thing on this side. -4 is exactly 9 away. So the numbers that are closer would be getting towards the middle. So if I look at this, that's an and inequality. We can clearly see that our solutions, all the x's, fall between 14 and -4. And if we want to be fancy with our set notation, we could do it like that. I'm also okay with you just doing it like this. And ultimately, we don't really need the fancy set notation. It's just something nice to practice with. But if we chose any number between -4 and 14, we guarantee that the distance between that and 5 is going to be less than 9, right? Pick one. 10. Well, that distance is only 5, less than 9. How about -3.9? Well, that's less than 9. That's, 8.9 units away. So we can see here that we have an and inequality. Moving on to the next one, the absolute value of x plus 4 has to be greater than or equal to 8. So I do note that we have the absolute value, but we don't have a minus sign. So this distance in between thing doesn't apply yet. So I need to rewrite a positive as subtracting a negative. Notice how I use parentheses here. That really helps me keep track of the two things that I'm comparing, the two things outside of the minus sign. So my absolute value and my minus give me the distance in between. So the two things, one on the left and one on the right of the minus, one of them is clearly x and the other one is -4. Now that distance that we're looking for is more or exactly 8 units. Okay, well, if we're looking for x and we're comparing it to -4, I don't know where x is on the number line because I don't know what x is yet, but I do know where -4 is. So if I can place -4 on the number line, I want all the numbers that are 8 away or more. Well, let's try to the right. So if I travel this way 8 units, that would bring me to the number 4. That one does work because it's exactly 8 away. If I want more distance, I should go away from that center. So these numbers here, like 0 and 1 and 2, they're less than 8 away. So if I want the numbers that are more, I should get farther away. I should do the same thing to the other side though. If I go 8 this way, because again, it doesn't matter what direction we travel that distance, we just want to travel that distance. -12 is exactly 8 away. So I'm gonna fill that in because it does work. If I want more distance, I should increase that from the middle. So I'd have to shade this direction. So I can see this is clearly an or inequality, right? We have all the x's such that x is either less than -12 or the x's are greater than or equal to 4. I'm sorry, I forgot. Less than or equal to 12. Now with question number 4 and question number 5, we are going to do them two ways. The second way that we're going to do them is very algebraic and it's my least favorite. So we should be able to fit this into our schema that we have before. So let's continue to do that. And if this way is complicated for you, we'll look at an algebraic way. So I see the absolute value in a minus sign. So that's the distance between. So I like to go ahead and put like two boxes around the things so I know exactly what two things I'm comparing. So you'll notice here, one of the things I'm comparing is 2x and the number 8. Now we'll come to that 2x in a moment, but that distance is less than 7. So the way that I'd represent this on a number line is I don't know where 2x is. I definitely don't even know where x is. So how do I know where 2x is? But I do know where 8 is. Now, the distance away from 8 should be less than 7. So this number right here, that's 7 away, in other words, 15, that number doesn't work. So I'm not going to shade it in. But all the numbers in between them do. Now, if I look to the other side, again, this way I could go 7 units. Now that distance should be less than 7, so the number 1 doesn't quite work. So I'm going to put an open circle there. But everything else on the inside does. Now the difference here is on all the other problems, our endpoint was exactly x, right? Because we were saying the distance between this number and x was more than 8. So like, I'm just going to use an easy example like with this one. If the distance between x and -3 was 7, if I travel 7 away, the number I landed on was exactly equal to x. Same thing over here. If I said the distance between this number and x was 7, if I go 7 away, this number must be x. But in this one here, the number we end at is not called x. This is called 2x, right? And the number on the other side, 1, that's not x, that's 2x. So in other words then, by a quick solve, the x value would be 1/2. And here the x value would be 15/2. So what we're saying then, the solution set, we can see this is an and inequality because they meet in the middle. We have all the x's such that the x's are in between 1/2 and 15/2. And we are not including 1/2 or 15/2 because that distance is exactly 7 and not less than 7. Let's look at number 5 in that same way. We'll note here on this one that the order is backwards, right? But we still see this absolute value subtracted by a minus sign. So it's still the distance between, but now our order is different. The distance between 5 and x is 4 or less. But does that really matter? I mean, if I would have said the distance between x and 5 was 4 or less, would that really have made a difference? Well, not really, right? Because distance doesn't matter the order. And that kind of reminds me, 5 minus x, kind of reminds me of how we started this problem up here, where it doesn't matter what order I do this. If I put the absolute value around them, the distance is still the distance, right? So if I go from x to 5 or 5 to x, that distance shouldn't really matter. So let's go plot this. I don't know where x is, but I do know where 5 is. So if the number x that I'm looking for has to be 4 or less, well, let's travel 4 this way. Now that number would bring us to 9. I can use 9 because that's exactly 4 away. I want that or less, and less would be getting closer. On the other side, if I go 4 away, that would bring me to the number 1. And the number 1 is exactly 4 away, and the numbers that are less would be getting closer to the middle. So I can easily see that our solution set here are all the x's, such that the x's are between 1 and 9, and we're including both of them. Now, the alternate way of doing it is if you recall back to Algebra 1, we have some like properties of numbers. Like if we recall, if I have the square root of a product, I can go ahead and just take the square roots of those numbers individually, right? Like think about the square root of, let's do 4 times 9. Square root of 36 is definitely 6, but isn't that the same thing as 4 times 3? And it works with division too. If we have two numbers under one square root, we can take the square roots of both of them. Remember how these rules from algebra only worked for multiplication and division? We also have those properties for absolute value. If there's two numbers being multiplied inside an absolute value, we can simply just multiply the absolute value of each number individually. Or same thing works with division. If I have a fraction inside an absolute value and only using division, right? These rules do not work with addition and subtraction. I could take the absolute value of the top and the bottom separately. So another way that we'd be able to do number 4 is we could use factoring to rewrite this. So on the inside, if I factored out the 2, we can see that I have this thing, the number 2, times another thing, which is this product of x minus 4. So that's what we have here, right? If I have a product of A and the product of B, I can simply take their absolute values separately. So I'd be able to take the product of the first number and multiply it by the product inside the absolute value of the second number. So what we could see then is by rewriting this, This is the absolute value of 2, which is 2. And then x minus 4 is less than 7. So here we could solve to get the absolute value alone. And now we just rephrase the same question. Rather than asking twice, or 2x minus 8, we've simplified that down just to the regular x. I think this is a little bit harder though, because we have to deal with fractions, right? So if we think here, we do have that classic x and the minus in between the absolute values. So this would be the distance between x and 4. And that has to be less than 7 halves. So if I started at 4 and I added 7 halves, which would be 8 over 2 plus 7 over 2, that ending point is 15 over 2. We don't want to include that because that's exactly 7 halves away, so we'd have to go backwards. Same thing this way to get closer. 7 halves this way. If I took away 7 halves, right, 8 halves minus 7 halves does bring me to the number 1 half. But 1 half is exactly 7 halves away. We want less than that. So by using that property, we still get to the same answer. It just really depends where you want to do that little bit of algebra. I tend to think it's easier on this rather than pulling out that factor, but either way is fine. If we looked at this one, another way that we could think about doing this using our properties is we could make it look more like what we're used to seeing, right? If I factored out a -1 on the inside, I'd have -5 plus x. And then I like to rearrange that as -1 times x minus 5. So then we have this product here. So I can take the absolute value of the first number and multiply it by the absolute value of the second factor. And we know the absolute value of 1 is just equal to 1. So we have rearranged this into the absolute value of x is less than or equal to 4. Absolute value of x minus 5. And that's what I like us to see. Does it really matter the order in which we measure distance? If I start at 5 and go to x, or if I start at x and go to 5, it doesn't matter, right? This picture here would be the same there. So there's another quick way to do it algebraically. But again, I think using the number line is great. So moving forward, now we're going to move on to some more complex equations where we have absolute values on both sides. So if we think about a sentence here, on the left side here, we do see a minus sign. So this is exactly representing the distance between x and 4. But rather than setting it equal to a number, they've set it equal to a different distance. So I'm going to say the same because of the equal sign. So if I look at this other side here, x plus 6, that's not written correctly. So I'm going to write that as x minus -6, because if we're dealing with distance, we want a minus sign. So I can see that's then measuring the distance between x and -6. So in other words, we're saying the number, we have these numbers here. We know where 4 is on the number line, and we know where -6 is on the number line. Whatever the x that we're looking for, it's the same distance away from both of those numbers. So in other words, if it's the same distance from 4 as it is from -6, doesn't it have to be in the middle? So let's figure out the total distance. So the total distance between -6 and 4, right? We use subtraction to measure total distance. That total distance is 10. If I took that distance of 10 and cut it in half, I get a distance of 5. So I'd want to travel 5 from the number 4 and 5 from the number -6. Oh, well, that brings me to the number -1. So the solution here is x equals -1. Now we're going to do that algebraically, but we're also going to be able to do this graphically. So when we think about this absolute value of x minus 4, which I'm first going to do in red, all we know is that that's an absolute value that's been shifted to the right 4 units. So the vertex is no longer at 0, 0, it's at 4, 0. And since there's been no stretch or shrink, we know that each side of the absolute value essentially has a slope of 1 or -1. So since I'm looking for a point of intersection on the graph, I'm going to plot as many points as I possibly can and connect them with a nice straight line. That's my first absolute value. We know how to graph that from our parent functions. This second one, which I'm going to do in blue, the absolute value of x plus 6, if we view that from our transformational knowledge, this has moved to the left 6 units. And again, the slope of each side is either a 1 or a -1 since we don't have a stretch. So we can see here that where did these two graphs intersect? Well, when I connect these dots, and I connect those dots, the point at which they intersect conveniently has the x value of -1. So we have two different ways of solving these. Algebraically, by setting distances equal and finding the midpoint, or graphically, by plotting both absolute value curves and seeing where they touch. Sorry, I just used that number line up there. So our answer is just -1. So moving forward, this now is an inequality. So what we're looking for here now is, if we kind of treat this as a sentence, the distance between x and 11 is greater than the distance, so I'm just going to pull back that sentence, than the distance between x and -3, right? Because we could rewrite this as the absolute value of x minus -3. I'm just going through that a little bit quicker then, because we've already kind of covered that in the first part. So with this idea then, we'll do the same thing. We know where -11 is on the number line, and we know where the number -3 is. So while we don't want those distances to be exactly the same, it would be nice if we could figure out what the middle would be then. So if we think about the distance between -11 and -3, that total distance is what, 8? Oh, sorry, I messed that up. Sorry, it's 11, not -11. That's what my problem is, x minus 11. So I just got to rewrite my picture here. So if I measure the distance between 11 and -3, that distance is a total of 14. So if I wanted to find halfway, the number 7 would be exactly halfway in between them, right? Now what we want is the distance between x and 11 to be more than the distance between x and -3. And we can see this starts to become harder now when we only use a number line. But the idea here, sorry, I have a wrong number. The distance is 7, so in the middle, that number would be 4, right? It's 7 away from 11 and 7 away from -3. So before we come back to the number line, I think questions like this are a little bit easier to look at graphically, which is why we want to have two different ways of doing it. So let's go ahead and graph this first one in blue, x minus 11. That's been shifted right 11 units. I'm going to go ahead and place that 11, and then the slope on each side is, of course, just going to be equal to 1 because there hasn't been any stretch or shrink. And on the right side here, I'm just going to have to estimate that. Our solutions will be on the left anyway, so you don't need to worry about that. The other side, this absolute value has been shifted left 3 units because of the +3. So I'm putting in my slope of -1 and my slope of +1. Notice where they intersect. Oh, that's kind of a bad line. But notice how they intersect right here at this x value of 4. Now that's not the exact answer, right? I want the distance from the number and 11 to be greater than the distance between the number and -3. And again, on the number line, that's a little bit confusing. So what we should look for here is now asking ourselves, when is this blue output, right? This represents a blue graph. When is this blue graph above, because it's bigger, right? Outputs that are bigger are above this red graph. Well, let's just go shade on the number on our graph where that happens. Where's our blue one above our red one? Well, our blue one is above our red one on this part of the graph. So what x values does that hold true for? If I choose an x value to the left of 4, so in other words, if I choose an x value that's less than 4, that distance is going to be greater. In other words, that's what we're looking for, right? If we think about this on the number line, if I choose any number over here, anything that I've just shaded in yellow here, the distance between that number and 11, right? If I think about anything over here all the way to 11, won't that always be more than any number over here to -3? And it doesn't matter which one I choose, right? If I chose this number here, if I extend it to the number like this one, the distance between that and 11 is clearly going to be shorter than the distance to this and -3, because -3 is to the left, and I'm going to the left. So our final solution set here would be all the x's that are less than 4. Let's try another one. Let's do this one graphically first. I'm going to go ahead and do this one in red. So x plus 2 has been shifted right 2. And we know the slope of each side of an absolute value that hasn't been vertically stretched is just going to be 1 and -1. So you'll see me putting in those slopes. And notice how I'm putting as many dots as possible because I'm looking for points of intersection. So I want to have a perfect graph. We'll move on to the next absolute value. The next absolute value is x plus 7. So that has also been shifted. Oops, I think I shifted it the wrong way. I'm sorry about that. I should have shifted it left 2 because of the plus 2. So then this one would have been left 7. Now what we're noticing on this one is that point of intersection wasn't perfect. It wasn't on one of the dots that I placed, but it still gives me a great grounding point. First of all, we should never, ever, ever guess what that point is. I'll never know. So instead of guessing though, we can at least visualize. What we wanted to see is which one is bigger here. Miss Pac-Man, or that inequality symbol, is eating this, the right side in blue. So we want the blue side to be bigger, right? If we're talking about outputs, bigger outputs on the y-axis are above. So where is our blue line above our red line? Well, we can easily see that happening right here. So our goal then is to figure out, well, what was that x value? Well, that x value where they intersect would represent when those distances are exactly the same. So if we think about this on a number line, when would those distances be exactly the same? And here I'm just writing them as a minus so I can see what numbers I'm going to place on the number line. So I know where the number -7 is, and I know where the number -2 is. So the total distance in between them, that's a distance of, what, 5? So then if I wanted halfway, half of that distance would be 5 halves. Right? So from here to the middle is 5 halves, and from over here is 5 halves. So I just have to think what number, if I was at -2 and I went left 5 halves, well, that's -4 over 2. So I get the number -9 halves. Or if I did it the other way, if I started at -7 and I increased, so I went to the right by 5 halves, -14 halves plus 5 halves also gives me 9 halves. Seriously, negative. So I know that middle point right there has an x value that's 9 halves. And I can see that I shaded all the inputs that are to the right of that. So I only wanted the x values that were greater than -9 halves. Right? And we can think about that on the number line as well. If we know where halfway is, if I want the distance between whatever number I place, which is going to be a star, if I want the distance from that star to -7 to be more than that star to -2, I should place that star on the right because no matter where I am on the right, the distance to -2 is always going to be less than the distance to -7. So those are the types of examples that we have. And again, when we start to get to these complex inequalities with two absolute values, I do tend to think it's a little bit easier to start with on a graph. But again, that argument of saying, if I want the distance away from my star and -2 to be less than the distance to -7, I want to place my star on that side. If I wanted the distance to be more, I'd place it on the other side. So that argument's a really good thing to review because, again, we're going through the notes here that are pretty quick. But that's our notes for today.